Alright, hello guys, it's me back again, and today we're going to be going deeper into redox reactions. Now this is still just a pretty self-explanatory lesson. You probably have already went through much of this before. So anyways, let's get started. So today we're talking about, once again, redox reactions. Alright, so to get started, I'm just going to introduce a pretty simple equation that you guys have probably seen before, hopefully, but it's just an arbitrary equation that we're going to use. We have iron reacts with hydrochloric acid to form iron chloride and hydrogen gas. So this is a redox reaction. It's also a single replacement where the iron is replaced by the hydrogen, and the hydrogen becomes diatomic. But essentially what's happening is, or what you can say we're doing is, there's a loss and a transfer of electrons. So the oxidation state, we talked about this in the previous video, is what we can mark in all of these. So the oxidation state of iron is 0. The oxidation state of the hydrogen in this one is, well, let's see, Cl minus, and we know that it is balanced, so hydrogen is going to be +1, Cl is going to be -1. We know in this case, we know that this is totally a 0, so that would mean that this has to be +2, and each of these is -1. Then we know that the hydrogen, when it's in the diatomic, it's 0. So we see here, we are going to find out, or we're going to mark those that have changed their oxidation states. So for example here, iron has gone from 0 to +2. And then we can also see that hydrogen has gone from +1 to 0. So in this case, iron is becoming more positive, right? It's becoming more positive, which means that it's losing electrons. And in this case, hydrogen is becoming more negative or less positive. We're going to call it more, I'll just scroll down real quick, more negative. And don't know if you can see that, but here, there we go. So we can classify this as a reduction and an oxidation happening in this reaction. And let's just quickly define these terms as well. So a reduction is the loss of electrons. No, it's not. Reduction, or actually, let me color code this differently. Oxidation is equal to the loss of electrons. On the other hand, reduction is equal to the gain of electrons. Right? So, see how I color coded it? This means that the thing that's becoming more negative is being reduced, while the thing that's becoming more positive is being oxidized. Now, it doesn't necessarily have to be going from negative to positive. It could go from, like, let's say, -2 to -1. That's also an oxidation. It's just becoming more positive or less negative. And same thing here, reduction, it could go from -1 to -2 or something, right? It could go from -1 to -2, or even like 0 to -1. All depends on what we're considering. Okay, so that is the simplest form of redox reactions. Now we can just translate our knowledge to understand what half reactions are. Half reactions, if I can find my pen. Half reactions are basically another way to write the components of a redox reactions. So components is what I would say. So these are the components of the redox reaction, and obviously the components of a redox reaction, it is very obvious. So you have a reduction reaction, and then you have an oxidation reaction. So let's take, just for ease, let's take this equation that we had previously used, and let's just use that. Okay, so looking at that equation, we see that, or we've already determined that there's a species that's being oxidized and there's a species that's being reduced. Now how you want to write it is by considering how much is being oxidized or how much is being reduced. So if you see, iron is going from 0 to 2. So iron has a transfer of 2. Or basically iron loses, here, let me scroll down. Iron loses 2 electrons. On the other hand, the reduction reaction is hydrogen is going from +1 to +2. It's going from +1 to 0. Sorry about that. I read the wrong thing. So hydrogen gains, if it's going from +1 to 0, there's a transfer of 1 electron. So hydrogen gains 1 electron. Let's scroll down more. So using this information, we can write 2 distinct equations. So if iron is losing 2 electrons, that means that it is originally in its regular form, right? And then it reacts. Basically now, it's in an ionic form, Fe2+, and loses 2 electrons. You see, I put the electrons in the product side because here I can scroll to the left. I put the electrons in the product side because what's happening is the species is losing the electrons. If it was gaining the electrons, like we'll see in just a moment, it would be on the reactant side. So with that, let's use this and find out what we're going to do with this. So the hydrogen is gaining 1 electron, which means that we're going to write it as this. It's going from an H+, and we're adding 1 electron. Oops. We're adding 1 electron, and we're actually not going to H, we're going to H2. So using this, we actually first need to balance this equation. So H2 has a total of 0, and what we want to do is we want to balance the equation such that both the charges also cancel out. So for example, you see on this on the above equation with iron, the charge on this is 0, the charge on this is +2, the charge on this is actually -2, right? Because there's 2 electrons. So +2 and -2 cancel out to become 0, and we have 0 on this side. Similarly here, we have a plus and a minus, but we have 2 hydrogens on this side, we only have 1. So what we want to do is we want to just stick on a 2 over here. However, now this unbalances the charges, because we have 2 plus and we have 1 minus, which should leave us with just 1 plus on the other side. However, here there's a 0 charge. So what we want to do is we want to tag on a 2 in front of there. Now we can finally get to our actual redox reaction. These are our 2 half reactions. This one and this one. This one is our reduction, and this is our oxidation. Now when we add them, we can finally get our balanced redox reaction, which I will put in a unique color. Redox. So all we have to do is we have to add the reactants to the reactants and the products to the products. And using, we're going to write a balanced ionic equation, which means that anything that's represented on both sides of the equation can be canceled out. So in this case, we have an iron, so we'll put the iron. We have 2 hydrogens, so we'll put the 2 hydrogens. We have 2 electrons on this side, but we also have 2 electrons on this side. So we're going to ignore the electrons. In fact, one of the motivations of redox reactions is to actually make it such that the full redox reaction does not have any electrons in it. And basically you can run through more practice with that, but you also want to have the electrons cancel out on both sides. So then we have iron 2 plus, and then we have hydrogen. So this is our balanced redox reaction. You can check out the charges as well. The charges actually, they don't necessarily cancel out, but they're equal on both sides. Right, we have 2 plus, we have 2 plus, and we have 0. So both sides are 2 plus, that works out. Both sides have 2 hydrogens, both sides have 1 iron. So that is how you make a balanced redox reaction. So in a previous lesson, we talked about titrations, and titrations comes up with redox reactions as well. And I'm just going to define once again what a titration is. It's basically you slowly add a solution at a known concentration to another solution of an unknown concentration to determine the concentration of that unknown solution. So basically, to determine the endpoint of this titration, usually there's a color change, and titrations are really used in acid-base reactions, but redox reactions can also be considered titrations. So one really important substance in the entire titration process is potassium permanganate. This species is really an important feature as it's used in redox titrations. Basically, this manganese, it starts out with a oxidation state of +7, but then it gets reduced to +2. So it gets reduced to +2. Basically, what's happening is that the MnO4 is being reduced to Mn2 plus. So, and this MnO4 minus, it's being reduced to Mn2 plus. So you see, when you're looking at the oxidation state of this manganese, it's going from +7 to +2. So this also shows a color change. So that's really important. This is usually basically it goes from a purple color, and I'll just scroll down real quickly. It goes from a purple, like a really deep purple color. Yeah, it goes from a purple color and it goes to basically a colorless fluid, or I guess you can say white. Alright, So we can go through an example of how this would be actually used in a redox titration. So let me just write this equation up. Let's say the reduction of this reaction, I'm going to write it in blue. Reduction. That is 8H plus MnO4 minus plus 5 electrons goes to Mn2 plus H2O in the liquid form. Then we also have, I don't know what this is, we also have our oxidation reaction. And that would be C2O4 minus 2 minus goes to 2CO2 in the gaseous form plus 2E minus. So now I'll say that we have 50 mils. We have 50 mils of NaC2O4, sodium oxalate, and it's poured into an Erlenmeyer flask. There's an acidified solution of 0.135. If I can just write 135 molar KMnO4, which is potassium permanganate, and it's titrated into the flask while the solution is swirled on a station and heated. So a typical titration. The solution in the flask is first colorless, but it turns pink. So it's going from colorless to pink. Right? So we had just previously talked about this, that when it's reduced, it goes from pink to colorless. Oops. Yeah. So we know that this MnO4 is going to Mn2 plus, which means it's being reduced. And so say it turns pink after, say, let's write it, turns pink after post 14.56 milliliters of KMnO4. Yeah, now this might sound a little bit more complicated, but trust me, it just gets easy because it's just math. So what we're going to do now is we're going to take this reduction and oxidation reaction that I wrote, and let's say that we're looking for the concentration of the oxalate solution. So the oxalate is, what is the oxalate here? That is the C2O42 minus, right? So we're looking for the solution of this one. So we're going to find a way to combine the reduction and the oxidation reactions. And first step to doing that is obviously we're going to KMnO4. We're going to balance these equations. Is it balanced right now? It's not balanced right now, right? So we have 8H plus, so there's basically we want to balance the electrons still. So we're going to find a way to do this, and basically we're going to multiply this entire reaction by 5. The oxidation half reaction. We're going to multiply this entire thing by 5. And why are we doing that? So that this becomes 10. And we're going to multiply this entire thing by 2. So when we do that, all we have left to do is, we know that these two things are going to cancel out. All we have to do is add them together. So we will get 16H plus plus 5 C2O4, which is our oxalate, 2 minus, plus 2MnO4 minus. And it's going to react to form two Mn2 plus 8H2O in the liquid form plus CO2, 5CO2. Now go ahead, pause the video, and check if you see how this is entirely balanced. If it's a little bit hard, just stop and go through it. And now what we can do is basically we can use this formula. Molars or molarity is equal to number of moles over volume. And we know that, well, we just determined that there's 0.135. Let me just find it real quick for you. We have 0.135 molar of KMnO4 over here. And then how much liters do we have? Well, we know we have 0.01456. 14.56 milliliters is equal to 0.01456 liters. So we'll find basically we're going to find the number of moles of MnO4, which is basically what we're going to do is 0.135, if this point would come, 0.135 is equal to N over 0.01456 liters. Now when you do the math, solving for N, which is number of moles, we'll get that N is equal to I'll write it over here because it's easy. N is equal to 0.00197 molar or moles of MnO4 minus. Of MnO4 minus. Okay? So now we have one piece of the equation. We know that we have that much MnO4 minus. Let's go back to our equation, shall we? Let's find the mole ratio between MnO4 minus and let's find the mole ratio between MnO4 minus and the oxalate. So you see here we have 5 oxalates for every 2 MnO4. So now let's go back to this number we have. If we have 5 for every 2 MnO4s, all we have to do is multiply this by 5 over 2. And then we'll get how many moles of MnO4 minus, or how many moles of oxalate we'll have. And that, if you do the math out, it should be 0.00493 moles of C2O4. Now we have one part of our answer. Finally, what we can do is we know that there's 0.05 liters of sodium oxalate, right? We had previously defined it somewhere over here. Yep, here we had 50 milliliters of sodium oxalate, right? So that would mean if there's an equal ratio between sodium and oxalate, that means there's 50 milliliters of oxalate as well, which would mean that we could use that to our advantage. Let's scroll back to the equation. We have 0.00493 moles. So if we want to find the concentration, all we have to do is 0.00493 moles over nothing but 0.05 liters. Obviously 50 milliliters is 0.05 liters. Finally, we'll get our answer as 0.0986 molars. And basically this is the concentration of C2O4. So with that, we have also not only found the concentration of oxalate, but we've also found the concentration of sodium oxalate. So that was just an introduction to redox titrations. Obviously there's more to do with redox reactions, and we're going to get into that with the galvanic cells and electrolytic cells. So stay tuned for the next video.